Um, I'm very pleased to confirm that our colleague Derek DeBar is joining us, who will be looking at the electric tracing side of things. He's head of corporate training at Chromalox, and I must thank him for getting up out of bed very, very early this morning, because it's probably around 2 o'clock US time. So thanks, Derek. Much appreciated for your support.
Good morning.
My name is Lee Clapton. I work in the Group Oil and Gas and Chemicals division here at Spirax Sarco. We'll be hosting one webinar per month from now until the end of December, okay, as part of the Thrust 2 initiative covering AIP1. So all information, copies of the webinar slides and recordings and the associated training packs will be available on the GOGC site within the SPB SharePoint area. Okay. The next one being on heat exchangers, which will be around mid-September. Okay, in terms of comparison between steam and electric, the comparison table that's indicated there gives a good overview of the differences between the two, where some are stronger, where one particular method of heat tracing is stronger over the other. In terms of reliability, electric obviously has sophisticated monitoring. There's possible damage, exposure to damage for heaters and temperature sensors on those particular circuits. But for steam systems, of course, you know, we've got steam leaks that are possible. However, they're easily identifiable because they can be seen. And steam traps, of course, do wear and or fail. Not doing steam a disservice, electric typically requires a little bit more thought, I think, around the design and resistance to flow in terms of amperage over the cable length, whereas steam tends to be sort of bolted on, added to an existing system, and there generally is a lot of rule of thumb regarding the design that often prevails. There's not really a set standard in terms of steam tracing design, albeit there are standards around the type of tracing that's utilised. In terms of suitable applications, I think it's fair to say where steam is, electric can also go. Maybe there might be some observation around safety showers where electric might be a better fit, but in terms of steam, we've got high limit cutouts that can be triggering off at 60 degrees C if required. And of course, we've always exploited the fact, I suppose, in the past that, you know, there's no fire risk. Installation is okay for hazardous area where we promote steam for refineries and chemical plants. But of course, electric now has all the appropriate accreditation and certification. So, you know, it really comes down to customer preference, past history, site maintenance capability, knowledge and experience. And it's fair to say that we can actually deploy steam and electric together. So it may well be that we can use steam for higher medium temperature applications and electric for perhaps more localized, shorter runs, perhaps applying heat into more complex product that has quite a difficult shape to trace around. Electric will probably lend itself far better. In terms of other mediums such as thermal oils and water, that won't be covered off in this particular session. So in terms of many industrial processes that require storage and transfer of fluids through piping and equipment, often these fluids rely on heating when its temperature drops below a certain minimum value, a maintained value as we call it. And this would require consideration on the installation of manifolds. So for example, here we've got a steam distribution manifold. So we've got steam coming in and we're distributing steam out through these tracer tubes here. And it's fair to say that not all the circuits are actually in use on this particular manifold, and that's perfectly acceptable. We don't have to use every circuit. After the steam's imparted its heat energy into the process pipe, it can condense. It will condense, and by that we've got steam traps there to discharge the condensate into the manifold, and then it's discharged into the main header. So additional heat input can be provided to the process pipe via a combination of insulation and heating. Okay. Now, not controlling heat loss can also result in damage to expensive equipment, for example, metering equipment. All right, it can impair the quality of the end product that we're trying to produce. It can cause solidification issues where certain products can't be reheated to get back into liquid, you know, and that is really a dangerous situation. So that's very sensitive. And then you've got liquids that have to be maintained at a certain viscosity so that it's easy to flow from one point to another. In addition, we've got to care for our equipment as well, because not everything is suitable for low ambient temperature. So if there's a particular material grade of valve or control valve or isolation valve, it needs to be heat traced, okay? And that needs to be heat traced even when maybe there's a shutdown. We need to maintain that heat content into that valve body. Otherwise, we run the risk of freezing, and if the system is not being properly drained, that causes expansion and then cracking. In terms of the steam trap population, I would say that steam tracing is pretty significant on any oil and gas plant. You're probably looking at 50 to 80% of the total application requirements containing steam traps. So steam tracing offers great opportunity for Spirax Darko. Selection of the correct design of steam trap is very important as well, because it may well be that we want to remove condensate as soon as it forms, therefore maintaining that steam tracer full of steam and not partially flooded with water. And depending on the application, it may well be that we might want to install a steam trap that holds back condensate so that we're gaining maximum sensible heat from that condensate that's held back within the tracer itself. So it's very, very critical that we apply the right type of steam trap for a given application. Now, at this point, I think it's a very good time to give an example just to confirm how heat tracing is designed and used. Now, this particular slide shows an extreme example, I know, but it's perfectly plausible with extremes of temperatures which are happening globally. We're seeing that in the news and in the press. So let's consider an installation in deepest center of Russia, and it could also be in northern parts of USA and into Canada as well, where the minimum outside temperature can drop to pretty significant levels. In this example, I've selected -43 degrees C. An 80mm water line contains water at 22 degrees, and that's what we're trying to control at. But the water process can mean that it can stop as well as flow. We've got a 30-mile-an-hour wind flowing across the going across the site, which will impact the situation even further. So as you can appreciate, the heat loss from that water pipe at 22 degrees will be pretty significant to the surrounding air, and it will lose it very, very quickly. So if we just look at a single meter straight run of pipe, okay, there's no addition of valves, fittings or flanges and no heat tracing or insulation, you would be looking at around a heat loss of around 300 watts per meter exposure. And that's pretty significant, okay? And that would be equivalent to something that's like a 0.5 meter or a meter diameter pipe under normal tracing conditions. That's the sort of wattage exposure that we would see, not from a 3-inch 80mm small OD pipe. So as you can see here, it's pretty significant. The first line of defense really would be to consider insulation. All right, there's many different forms of insulation, different design thicknesses and efficiency levels. And we're not surprised really from our experience that a lot of our customers will spend a lot of time thinking about the type of tracing, whether it be steam, whether it be electric, working out the tracer runs, trying to make everything as well designed as possible. And when it's installed, someone's forgotten about the insulation. And that really is detrimental to the whole performance of the system, because the insulation really supports the heat tracing, whether it be electric or steam, very well. So that 1 meter water, 1 meter straight length of pipe containing that water would be expected to freeze probably in less than an hour, based on this scenario. And then you've got the expansion of that water as it converts to ice and freezes, and that puts stresses on welds as well as the pipe itself. So the natural thing to do is to apply insulation as our first line of defense. And using this will really impact on the heat loss. It will reduce it significantly. Then we can consider then supplementing that heat loss with our tracing system, whether it be electric or steam. And we're driving down that heat loss to a more manageable level. That's what we're trying to do. The insulation could be Rockwell, that's pretty well standard. And in this scenario, we're looking at around 50 millimeters thermal insulation. So what we've basically done here by applying the insulation is actually buying us time. We're probably giving us 10 or 20 hours without any form of additional heat before that water really drops to freezing point. So in terms of the impact on the overall reduced heat loss, we're looking at around 15 to 25 watts per meter. So that's a pretty significant saving just by applying the insulation. And if we increase the insulation to 100 mil, I would expect that to be at least halved as well. So that gives you a good idea of the importance of it. So in terms of heating medium, we will be using typically steam within 2 to 17 bar. More often than not, the range is between sort of 3 and 5 bar. Really heavy viscous products, for example, bitumen, may require more intensive heating and higher pressures because we're running that sort of quite viscous product, quite thick product from over quite significant distances. But as I said, for most tracing applications, it's undertaken at lower pressure because, of course, then we're benefiting from the larger heat content, the HFG, that is achievable when that steam condenses. Tracing steam at lower than 2 bar is risky. It's not recommended because that pressure loss can be achieved quite dramatically, especially regarding trapping distance and overall condensate removal, especially when we're discharging into headers and maybe having a lift after the steam traps. If we need to deploy pressure reduction, we can do that via a pressure reducing valve. And I'd say that virtually every application I've been involved in, it's been a closed system. I suppose if there's an open system, then the chances are that condensate that's collected might be contaminated in some way. And there's a typical condensate system there working in tandem with the steam distribution system, discharging the condensate into the condensate return main. In terms of what the system looks like in terms of design, I've put together this P&ID, and as we can see here, we've got our main steam header. This is where we're drawing off our steam to feed our steam tracing circuit. The connection should be made off the top of the steam header because that is where the steam is at its best, is most driest. We then create our tracing steam header, at which point we take off the low pressure steam, into our steam distribution manifold. And that can be a fabricated manifold of 4, 8, 12, 16-way connections, depending on what's required, or indeed it could be our own forging that we're all very familiar with. In terms of the tracing connections, we're feeding steam into this from the top and then distributing out into our process pipe. So our tracer lines are attached to the process pipe as close as possible. okay, and then wrapped in insulation, wrapped in insulation to protect and keep that heat in. The steam circuit can then go to a separate collector manifold as shown here, or it can split off to an adjacent collection manifold here, which is then taking condensate from another distribution manifold elsewhere on the plant. Condensate manifold there is typically of that design, and you can see here we've got the steam traps fitted, ready to receive the condensate after the steam's imparted its heat energy, and the condensate then connects up into our condensate header. You can see here that we've got a lone tracer. This could be an instrument tracing line, giving a little bit of frost protection, preventing freezing. It could be anything like that, but this is attached to a process pipe. And it's true that we could put a four-way manifold in here and then disconnect the 3 connections on it, but that's a little bit extreme. A simple steam trap there with a pipeline connector having its own form of isolation will be exactly what the client wants. He doesn't have to then put in additional isolation valves. So in terms of the types of trace heating, it's all about really maintaining heat that is already in the process. Okay, so basically we're balancing the heat losses from the system. We're looking at frost protection and also heat addition. Not many of those typically we get involved in, but you know, we can apply heat addition through jacketed tracing is a good example, which we'll touch on in a moment. And these are the categories of the different tracing methods that we'll be looking at shortly. Some of those may or may not be familiar to you. So in terms of critical tracing, this is basically where we've got to prevent solidification. We've got to protect the product quality, you know, it may well be that we might have to control that product within a certain temperature band. Often higher temperatures are involved, and if that's the case, then we might have to apply high efficiency tracer tubing, or indeed we might have to increase the number of tracing pipes around that pipe. Important equipment comes under critical. I don't think that generally gets thought of really. We always think about the product flowing through the pipe, but you know, critical tracing can also mean tracing of equipment that if damaged or fails, puts at risk safety and control and efficiency of the system as well. In terms of dedicated controls, we can put our TA10Ps and TA10As on the steam circuits, and those will maintain a set point, okay, for that product temperature. So on the situation here, that we've got a probe that's inserted up inside the insulation, detecting the product temperature. So if it falls below a certain set point, the valve opens up to allow more steam into that steam circuit. And likewise here, we can detect ambient temperature. Again, if there's a drop in ambient temperature, the valve will emit more steam into that tracing circuit. So we've got very localized control using our dedicated equipment. For ultra critical equipment, jacketed tracing really is the way forward at this present time. There is another option open to us, which we will touch on very shortly. But critical tracing via jacketed pipes is still used extensively. There are commercial implications. It's very expensive to install. We're looking at a fabricated jacket that fits around the process pipe. We've got steam entry connection there via a flange connection, a jump over which needs to be insulated as well to get steam into the next jacket. Typically on these, you'd be looking at runs of no more than 6 meters. They would be fitted in series like this, and really used for heat up or heat addition, and for maintaining temperature in critical areas. It outperforms in terms of temperature capability when compared with, say, bare tracers or high efficiency tube tracing. But when you're up against conductive high efficiency tracing, especially with heat conductive compounds, commercially you're going to be struggling on price because jacketed tracing is very, very expensive. In terms of the overall length, typical guidelines set by the contractors are around about 30 meters, at which point then the whole circuit starts again. And it's very important that we employ air vents as well. In terms of non-critical, winterization and instrumentation, these are the other categories of tracing that we come across quite regularly. So non-critical is really where we're just replacing heat emission losses from the pipeline, promotes the flow of product through the process pipe, perhaps not within a tight control in terms of temperature band. The steam traps that we would apply on there would be typically traps that might say hold back condensate, so we control the waterlogging of that steam tracer pipe, gaining maximum sensible heat out of it. It's not important that we remove condensate very quickly. Winterization, or frost protection as it's often called, again, this is typically around sort of water-based products. Controls are recommended to be the air sensing type to simplify the installation. Instrumentation, often to protect valuable equipment such as flow meters. This would be typically 6mm, 10mm OD copper tube, something like that. Very easy to bend round a particular product rather than trying to use 10mm or 12mm OD tubing, which really is difficult to bend. And also we want contact between the tracer tube and the equipment that we're trying to protect. So in terms of the good, the bad and the ugly, this slide here shows a good representation of how tracing should be laid out. There's an abundance of copper, as you can well imagine, on a typical refinery and chemical plant, so copper is used quite extensively. And this here shows that the tracer tube is laid out with a fall in the direction of flow to allow condensate then to be reached to the steam trap with ease. It's obviously sensitive, whatever's in that equipment, because we've got spacer blocks here shown. So we're just keeping the tracer line off the surface of the equipment. We don't obviously want any burning or any hot spots that might damage the product going through it. And then of course that will then be insulated. The bad here, there's not really any thought, it's just laid on, it's heating up the atmosphere more than it's actually imparting heat into the equipment. There's no real thought about the length of tracer and the impact on pressure loss. It's just a case of get the tracer on there and it will sort of do its job, but it's not. It's got to be thought of, it's got to be laid out correctly and providing the right contact. In terms of the ugly, this is where steam lances are often adopted, and it's really down to the inefficiencies of the steam system. And we see this generally around viscous products where it's difficult to flow. The tracing system isn't working correctly, whether that's block tracers, ineffective steam trap operation. But what they do here is they connect up a rubber hose here onto the steam header, and consequently put a metal lance on there, and then the valve just open up and we just put steam straight into the insulation to get the product flowing. Whilst we're overcoming a particular problem there, the tracing system needs to be looked at, and also of course there's no steam traps on this, so we're just putting water into our lagging, and waterlogged lagging is not good. Here's some TA10Ps on controlling, this is on a jetty, this is controlling the flow of product, either going out to the ships or disembarkation of the product from the ships onto the facility. But you can see here this particular product here with the heat image is working okay. We've got the controller fitted there, but as you can see here, we're 50% down on our controls activity here because there's no head. It's actually being taken apart and not being rectified. So in terms of tubing design, basically fundamentally we have our bare convection heating, which accounts to about 70 to 80% of all the steam tracing that we see on site. Bare metal pipe, whether it be copper, carbon steel or stainless steel, is still used, as I said. It can be used across a wide temperature spectrum for all applications involving low, medium and high heat requirements, maybe plus 200 degrees C. If they're not installed correctly, then, or if the lagging becomes waterlogged or damaged, we can get corrosion problems under the insulation, and that's magnified, of course, in the presence of air. Certainly from our experience, this can be at the base of vessels, pipework supports, and of course underside of horizontal pipe runs and pipe elbows, to name just a few. In terms of tracer run, we'll be looking at around 45 to 50 meters circuit, at which point then we terminate with a steam trap and then the circuit would run again. In terms of tracer tube diameter, you wouldn't necessarily go above 3/4 inch. Because then bending of that tubing and installation makes it quite difficult. We'll be looking at seamless Schedule 40. I've never known Schedule 80 pipe, to be honest, be used, but Schedule 40, and it's installed obviously with insulation. In terms of expansion, the tracer pipe will, without doubt, expand at a much greater rate than the process pipe itself, and that an allowance needs to be put in for that, because otherwise we're going to break joints. And as you can see here, the preferred method here is to put the expansion joint around a flange connection, as shown there. Or if we've got a long run, no flange connection, we could put 4 loop in, just to give us an expansion capability. Putting expansion in like that and like that just creates a low point where condensate collects, and we all know the reasons for not doing that. In terms of tracer install, there's some certain guidelines around that. Certainly, the tracer itself should be installed at the bottom of the pipe, ideally where we're looking at multiple tracer install, looking at 30 to 45 minutes and 30 to 45 degrees. Really, we should be tracing at the top of the pipe, because the chances are that there's likely to be air there and we don't want to be heating up air. In terms of attachment, we want to get that tracer tube right as close to that product line as physically possible, and then we put bands in around 450 millimeters max. Stainless steel wire can be used, but what actually happens is that the wire can snap over time, and then we get a situation where we get the pipe sagging and creating low points. On vertical pipes, it's good to lay out your tracer tubing as shown there, so it falls in the direction of flow. Bad practice here to create a low point, but we still see a lot of this. You know, it's best to lay it out like that if we can do, to come in from a horizontal point of view with a gradient. And likewise, where we're controlling temperature around winterization of, frost protection of large control valves and isolation valves, is to come off the steam tracer line and independently trace around the pipework there and put a steam trap on the bottom there and a steam trap on the bottom of the tracer itself. Good heat efficiency. It's very important that when we're tracing horizontally as well, we don't forget around the flanges, there will be dead legs around this point here, and we've got to get that tracing tucked right inside if we can do. In terms of dead end of product line, it's very, very easy during the installation to actually forget about the dead end, and it's very important, because what more often than happens is that tracer line there will then be taken straight the way down here, and we forget about this dead end condition. The oil is still flowing here, and of course we've got a stanchion here that will actually absorb a lot of the heat, so we've got to offset that. So that tracer tube will be 1/2 inch, as this example shows, 1/2 inch tracer tube, and it's drained via a steam trap. So it's critical we get that oil flowing into that shower tube heat exchanger, and we put on a steam trap there that's discharging condensate as soon as it forms. Steam goes into the tubes, okay, and the oil passes over the tubes, and then the heat from the steam is passed into the oil to keep it up to the required temperature. Condensate from the tubes is then passed to a steam trap, or we can pump it if there is high back pressure. In terms of tracer install, here's a fine example of where, with all due respect to the customer, they've done really well, they've insulated, but we've got dead parts where insulation has stopped. It hasn't carried on for the reasons that we can see there. It's just too difficult to get that insulation round, but unfortunately it needs to be done, and and we point this out to our customers. And from the heat map here, we can see the amount of heat that's given off from that tracer. It's pretty incredible, and all we're doing there is just not putting it into the product. We're heating up the atmosphere. In terms of the modern types of tracing that's available now on the market, this really does take it to the next level. Ultimately, what it does for us is it actually reduces the number of tracers required, often when we've got high heat loss that we've got to offset. These tracers are pre-insulated, high efficiency, and can cope with narrow bands of temperature. So it fits nicely and very comparable against electric tracing. The benefits here, of course, is it can run for much longer circuits. So you could expect to get a tracer circuit of 100 meters at least out of a high efficiency tracer tubing without the need for additional valves and trapping. So it really does complement steam very well. It's got it's got a yellow coating on there as well, just giving sight an indication that there's something hazardous in there. And that's something we don't see generally with bare tracing, and there are safety issues around that with skin burns. Conduction heaters will certainly give jacketed tracing a good run for its money, especially when using compound heat conductive paste. Okay. Certainly on the commercial side, it's much less expensive to put conductive tracing in than jacketed tracing. In terms of steam trace heating, I want to really, before we get onto the electric, just really reinforce that, steam tracing, there is a lot of equipment that needs to be installed. It's not easy, and I don't want you thinking that it's easier than electric, because it's not. We need to think about steam distribution manifolds, whether that's forged, whether it's fabricated, it needs to be collected, okay, at some point, with all the different steam tracing circuits. We need to think about, maintaining good quality steam before it's distributed out to our product pipes. We need to think about control. How are we going to control the heat tracing? Okay, whether it's around the equipment or the maintaining temperature of the product flowing through the pipe. Do we put in OD tubing, carbon steel, stainless steel, copper, or do we go with the high efficiency tracer tubing, or maybe jacketed tracing? Condensate manifold needs to be put in place, because we need to collect that condensate and reuse it. And we need to then select the right type of steam trap for that particular given application. How do we monitor the steam traps? Because if it's on critical tracing, we want to make sure that that circuit is right, it's up to temperature and it's doing what it needs to do. So we can put in ISA 100 steam trap monitoring systems. And this is a fine example one here done recently for the Fideli complex, whereby ISA 100 was accepted for its excellent protocol and security. Insulation, again, as I said, hand in hand, additional tracer tubing and insulation makes for a good, efficient system. So that gives a good, I think, overview of tracing. What I want to do now is pass on to my colleague, our colleague Derek DeBar, who will now cover the rest of the session on electric.
Okay, hey, thank you, Lee. Trust everyone can hear me okay? Silence would be yes?
Yes, we can hear you.
Okay, thank you all. And thank Lee and Helen for having me here. I'll walk through a quick introduction to electric heat tracing, and because we're focusing on oil and gas and petrochemical, I'll also illustrate some key applications and some terminology and some of the stuff in that market. As you'll notice, electrical heat tracing, a lot of the terminology is very similar. You talk about circuits and runs. It's very complementary, and you can actually supplement electrical heat tracing for a lot of the steam tracing applications. Obviously, steam has to be present or generated to use steam tracing, whereas if you're in more remote areas and stuff, electrical heat tracing might be a viable option for you. So with that, I'll get started. I mentioned before, installation is actually pretty similar to steam tracing, but there's a lot more maybe design considerations early on, how to lay it out, circuit lengths, that type of thing. As an illustration to everyone, you know, not only petrochemical and oil and gas, you know, I mean, this goes to, you know, building and construction, roof and gutter, drains. I mean, they use electrical heat tracing in a variety of applications, which makes it very versatile. So it's kind of handy for everyone. To start with, you know, there's not a whole lot of variety in electric heat tracing. You'll basically have two kinds. You'll have a self-regulating heating cable, which we'll focus on here. A constant wattage, which there's many different kinds. There's, you know, polymer based. There's MI cable, which we'll talk about specifically for oil and gas for higher temperatures and more hazardous and high temp critical robust design. We also have, you know, commercial heat tracing and stuff I mentioned, which we're not really going to focus on for today's presentation, but we're going to focus on the self-regulating stuff you see on the left and the mineral insulated stuff you see on the right. Again, self-regulating stuff, we'll talk about kind of the fit, form, and function. The MI cable is for your higher temperature, more robust installations, and even for adding heat into a process. So starting with the self-regulating cable, I think it's important to understand how it actually works, because it falls into the design and support and how you offer solutions to your customer. It's really simple, actually. Electric heating, you've got two conductor wires you see on the top left. You'll see a little, we often refer to it as a dog bone design, where it's an extruded polymer black, carbon black. It's basically impregnated carbon and polymer. And what that actually does is it creates conductive paths. So you're running power to the two conductor wire there. The carbon impregnated polymer, the carbon black, is the actual resistor. And what happens is, as it creates temperature or sees temperature, quite frankly, if the pipe's hot or whatever, it expands. And as it expands, it changes its actual resistive properties of the cable, which allows it to be, quote, self-regulating. So a 5-watt cable at 50 degrees is maybe a 3-watt cable at 100 degrees. And therefore, as it increases in temperature, it inversely, the output decreases, which allows for the self-regulating properties, which makes it really useful in the field for control, overheating. You can overlap it, and you can cut it. It can be cut to length and installed on site, which makes it really handy for remote applications and specifically oil and gas. From there, there's a grounding mesh, which is no different from, you know, standard electrical conductor wire, where you'll have, you know, a ground, and then protective jackets, fluoropolymer, or even a Teflon coated jacket, depending on your application. As I'll focus on all electrical heat tracing, it's electrical. So based on your output, whether it's 3, 5, 10, we even make 20-watt cable on the higher temp stuff for self-regulating. It's important to remember that you have a definitive amount of amps output to the cable. So that's where the circuit lengths and the breakdown of cable in the layout become very, very important. So if there becomes limitations on length and size of cable, much like we were dealing with, say, quality of steam and condensate and having to address that. On the electrical side, you have to address run length. So, you know, a 200 or 300 foot pipe or run might be a limitation, or you have to break it into 2 circuits, and then layout becomes very, very important. So these are things to consider, especially when you're designing the installation of cable before you go to install it. You'll need to know on the bill of material how many connection kits I need, how many end seals, how many power points, and then that becomes your circuits as you lay out your cable. Now, talking about types of cable, it depends on the types of application. And we have cable to fit most applications that you will come across in the oil and gas world. To start with, the SRL is pretty self-explanatory. It's the self-regulating low temp cable, which would be for, as Lee had mentioned earlier, the different types of applications. This would be more of your freeze protection application. So maybe water lines, maybe overcoming temperatures of less than 150 degrees F or 65 C. Again, very common for freeze protection. The limitation becomes the polymer. If you start exceeding those temperatures, then you start to break down the cable, and problems ensue. So we make an SRP, higher temperature cable. And it's also important to point out on electric heating cable you'll notice 2 temperatures highlighted on any of these, and one is a process temperature, which would mean electrified and the cable is actually outputting heat. There's also an exposure temperature, because in some scenarios where you're doing freeze protection, maybe when the system's up and running, the cable is exposed to higher temperatures than what the cable is designed for, and that's what you have to consider as well. So we make an even higher temperature cable, which is our SRME, which fits the majority of your applications. Lee mentioned viscosities, keep things flowing in the oil and gas world. That's very important. If you're not worried about freeze protection and pump offs of condensate tanks and 3-phase separators, you're keeping the petro product or engineered chemicals in a refinery flowing and moving. You would go with a higher temperature cable, such as an SRME, which is good up to 215 C exposure temperatures. Similar to, say, the steam tracing with the headers, and then you run off to different circuits. We have to have power connection kits, junction boxes, basically. I'm going to highlight one of a few of our choices. This is our most common and top of the line connection kits that we do offer. We call it our U series. The U actually stands for universal. Universal for the fact that globally we've gotten as many third-party certifications that are available for installs in any country. If it's a lot of times with electrical heat tracing, or any heat tracing for that matter, it's designed by an EPC or an alternative company, and then it gets on site, which could be in a different location, in a different country, and this ensures that we meet those area classifications for all that. Talk about them just a little bit. They're actually quite simple once you start to install and get used to those, and we have installation videos and stuff for anyone to check it out. But anyone familiar with electric in general, you have a junction box, you have power coming in, you have the cable where it connects to the cable. It's actually DIN rail mounted WAGO terminals on the inside. The cable itself, though, after it's installed, which is very mechanical, like a lot of heat tracing installable piping, it'll have we call them the pipe stand, which you'll see there on the top right. The cable comes up through a grommet. You splice the cable from there, then you install the junction box, and then you have electrician come out and connect the power, make sure everything's right. Do a cable test to make sure that everything's set, no ground faults, all that, and then you move on. You're good to go. Another thing I did fail to mention on the last slide too, in the universal and any of these cables, our standard off-the-shelf cable is rated for Class 1 Div 2, which meets 95% of your applications in the oil and gas and petrochemical world. So that's not so much a concern, although where we do fall into a little bit of gray areas is a lot of customers, and I get this a lot, where they, it's a hazardous area. Well, it becomes very important, especially in electrical terms, that term hazardous can be very relative. Is it class 1 div 2 or class 1 div 1? The reason I bring that up is there aren't a lot of div 1 area classifications, and if they are, they're small. So you think of like where a wellhead is, or maybe a specific process or tank. But when you get a certain distance away, you no longer need to go with div 1 rated stuff. Now our standard off-the-shelf stuff is div 2, but that's why I'm kind of leading into mentioning that we do have div 1 rated cable. You just have to ensure that it has the proper markings on the cable. Again, we have the low and the medium available. Not much more to talk about than that. The ratings are all the same. It's rated for those hazardous area classifications. But what is different is the connection kits. They'll have the epoxy packed sealant, Chico, I think is the term, in the EYS seals. And so the connection kits become a little bit more cumbersome and difficult and permanent to work with. But that's kind of the differentiation. You'll occasionally come across that in the oil and gas world. Again, 95% of the applications will all be just the standard off-the-shelf stuff with the U series. But it's important to bring up that the option is available if you are closer to wellheads or other applications that require div 1. Moving on, mineral insulated cable. This would be for even higher temperature applications, and also for where in the properties of self-regulating cable, it decreases with temperature. This would be a constant wattage cable. So maybe if you need a little bit more thermal input, probably if you're designing a system where you have higher temperature, this would be closer to what you might be used to with the steam tracing. It's semi-rigid, it can be bent, and it is for installation. With all this cable, both kinds, you need to ensure you're Lee mentioned deadheads. You want to obviously trace all the way to that. You want to put service loops, especially for splicing and putting the cable, but also you want to, in the layout, ensure that you have places for expansion, because the cable will obviously expand and contract as temperature sees it. The MI cable, however, again, 2 conductors, you can get single conductor, but then you have to have power connection on both ends. It's often referred to as engineered cable, and to kind of unpack that a little bit, it is made to length. So where the self-regulating cable, you can bring out spools and spools of it to the job sites and remote, and it's really easy to work with. This takes even a little bit more thought and design considerations when laying it out. Obviously, more critical applications, higher temperature. You kind of get that from Lee's demonstration earlier. Again, meets all area classifications, class 1 div 2 and div 1 for your oil and gas applications, and I'll show you some examples of that as we go forward. Something that Lee kind of mentioned in his and holds true for our product as well on the mineral insulated cable, and as you can see in the bottom right, the gentleman installing it on the pipe, the layout, it's obviously a smaller profile than maybe steam tracing. You can get 20 to 40 watts a linear foot, but you also, in installing it, is very similar. Heat transfer cement or paste should be applied as well, and that's simply to dissipate the heat. If you're dealing in higher temperatures, you want good heat transfer and conduction through to the pipe and the metal. So something to point out with both kinds of heat tracing, quite frankly. So it just comes part of the design. Examples of installations there and on some of your facilities. Tanks, piping, really common. You can mechanically attach it or use the paste, and then you space it out. Also, this cable is referred to in other worlds as direct burial. So if you've been to shopping malls or walkways and stuff like that, and they're heated, it's the same stuff buried in that. So real quick, that's the 2 main kinds of cable that you'll come across in the oil and gas world, and hopefully that gives a high level illustration of fit, form, and function of similarities and to steam tracing and provide to that. Again, mentioned before, this is electrical. Steam tracing has control. We are no different. The electrical will have control as well. pretty simple. We can do thermostats, very similar to what you may be used to. You can do the big differentiation is the type of application. So you can have thermostats that are ambient sensing for, say, freeze protection most commonly, or in more critical applications, you'll have line sensing, thermostats, RTDs, and then wired back. You can get thermostats and single-ended in our power connection kits, which kind of eliminates more connections, more potential for problems. You get individual circuit protection, and then kind of a good, better, best scenario. I wanted to illustrate. This is our DTS, our digital thermostat, which is pretty industry standard now at this point in the oil and gas world. It's a single point use. It's that power connection or that junction box I talked about earlier. A little bit bigger design because what it has is an SSR, a solid state relay, for switching the power on and off. So you got control, temperature indication all in one spot. Especially in remote locations, this is really, really popular, and people utilize these even in retrofitting a lot of scenarios. The design itself, without going too far down the rabbit hole of electrical control, but it being a solid state relay, we're able to pulse the power on and kind of ramp it up. And you may or may not be familiar with electrical heat tracing, but inrush current is a big concern. You think of the properties of self-regulating cable being dependent on the temperature and that carbon black matrix. If it's upon startup, there'll be an inrush current that can trip breakers and things like that. This eliminates that and has kind of a soft start, which is really nice. And then our control panels obviously cover that already, but for a simplistic design, this is the way to go. It would be a shame not to mention it because I know Lee had some maybe poor installation illustrations of heat loss and stuff in some of his catalog or in his presentation. Qualified electrician needs to wire and terminate to all of our electrical heat tracing. I would strongly recommend that because in the oil and gas world, oftentimes we see where that is not the case. So we have tutorials and design work on that, and I just wanted to point it out to everyone to make sure that is part of your consideration in offering electrical heat tracing designs. Oftentimes the mechanical or the insulators would be the ones installing the cable, and then you have electrical come out and complete the process. Taking control just a few steps further here before we get done, we do have what's our ITC, kind of back to the off-the-shelf items. This is 1 and 2 loop stuff. So now we're taking the sophistication of our control a little step further. These are really nice because they have load management, temperature indication. When the load management does is actually monitors and monitors the health of the cable even when it's not running. So you think of the summer months and stuff when the stuff sits. One of the last sessions, a question came about reliability and we'll say the maintenance of heat trace. If it's laid out properly and put on the pipe, I mean, it's designed to last for years with virtually no maintenance. But you do need to monitor to make sure that something hasn't happened, that somebody hasn't replaced the valve and cut the cable, or damage to the cable has occurred outside of just normal operation. This again, 1 2 loop off the shelf. We have a step up from that is AS, LS, IT, AS, IT, LS, again, ambient sensing, line sensing, depending on your application. And we make them in larger buckets of 6 for expansion. So you can see where it becomes very easy to compile your entire system. Straightforward, easy, set out your circuits. We can take it a step further with BACnet, your building management systems, and because it is electrical, you can wire it into a DCS and control it remotely. Pretty simple to do. We have wireless available as well, although I would point out the caveat that a lot of these facilities and sites are sometimes wireless isn't their preferred method, but just want to mention it, and got a lot of options and a lot of availability for design and placement. So real quick, as I'm running out of time, back to the type of cable and installations and in the oil and gas world, couple common applications for electrical heat tracing. Again, a lot of times these are remote sites, but there's just as many in a refinery or collection facility as well. You'll hear terms such as knockout tanks, heater treaters, especially in the oil world. So knockout tanks, what that is basically, where if you're in production, knockout tank would be with maybe a condensate would be considered a knockout tank. This is where particulates and fluids that you don't want in your process, say gas processing, it gives a place for that to collect, and then you can address it and separate it from the process. Heater treater is very similar to that. If you're doing like an oil production or a well, you want a place for the particulates, the sand, the rock, the sediment, and stuff that you don't want to put into the pipeline to fall out. And pretty common, either if you're trying to keep that stuff flowing through heat trace freeze protection, or in the case of heater treaters, you're actually creating a heat profile that causes the interfacial relationship between the carbon molecule and all those particulates to release. It'll actually release the particulates and get them out of the way. And you'll see this all across oil and gas production facilities. And then you'll find underneath the insulation, there'll either be, we have obviously direct heating methods from our other products, but heat trace is quite common. And if it's not part of those tanks, it's a part of the piping to and from those tanks. Some of the other applications that are common and actually becoming way more common, and this is actually something I pitched 10 years ago. You still got the knockout drums, and the flares are becoming more and more not welcome, especially closer proximities to housing areas and cities. The vapor recovery, so you can't flare stuff anymore. So now there are designs to and processes to collect the gas from wet wells and stuff, and all of that piping and stuff will have some form of heat tracing or thermal input, whether it be steam or electric, to keep that stuff moving and running and keep everything in good standings. Here's some other examples of that. I mentioned before the particulates on the left. This would be sand catchers, pretty much on new producing wells. Get the heavy, thick stuff out before you start producing. Again, you can see the heat trace installed there on the left to drip tanks and condensate tanks, which you can see there in the middle. Very common in the upstream side of oil and gas production. As you're flowing the product or producing the gas, a really, really common application for electrical heat tracing, and I would assume probably for steam tracing, although if you're remote and in production, steam may not be as readily available. Electric becomes an easy option for what we call dew point and say gas conditioning. That term comes up a lot. Gas conditioning is simply thermal input into the gas. When you're dealing with compressed fluids such as natural gas or production and all that stuff, they're compressing it to move it into the pipeline or even simply coming out of the ground, quite frankly. You'll become familiar with the Joule-Thomson effect, which causes endothermic situation where as that gas expands and depressurizes, you're going to have freeze ups. If there's any water molecules in the production or gas, it will start to drop out of the air, drop out of the fluid, and cause freeze ups on your valves, your sensors, and cause problems throughout the whole process of upstream to downstream, and that's where electric heat has a really good position for that, and offers a solution to the customer. Here's some examples of that. You can see the icing of the valves and the condition on the left. You look down, really good install in the middle where you've got an expansion valve off the T there, and then that's where you want to add more cable, and that becomes part of the discussion of design and a little bit more thought into how you install that. Moving on, I mentioned condensate tanks. Any production well or along your production pipeline, you'll have condensate tanks, drip tanks. Again, this is the same thing as basically a knockout tank for these fluids and products to collect. They can pump them off and address them later. Many of you may be familiar with the term produced water. This is, oftentimes where that's collected. Produced water is simply the water and one of, I think last I checked, 284 different possible contaminants out of the ground that they have to collect it somewhere, because you can't just throw it out on the ground and let it vaporize and then they address it later. These tanks are all across the countryside in any country, and they'll require heat depending on their geographic location. Of course, if they're in Texas, not so much, but if they're up in the oil sands of, say, Canada, or in Russia or something, they certainly will require heat to keep that from freezing, because you've got to pump it off and address the fluid. Moving on, I did mention pipelines. So again, with the Joule-Thomson effects, JT effect as they often refer to it, when you've got compression in pipelines, all your valves and kind of the interconnecting piping and stuff like that, it's all going to have potential for this to occur. Adding BTUs into the piping, again, Lee focused on this quite well earlier. Insulation, but even with insulation, there's loss. This is going to occur regardless of the insulation. So you're going to need to put added BTUs, thermal input, into the piping. So steam is an option. If steam's not an option, the electrical heat tracing is a great alternative, and that's kind of the point to bring it up, everybody on the call. What that kind of looks like, and I know, and maybe a little bit of a shameless plug on our side about decarbonization. We are electric. On the left, these are actually tanks for pipeline injection for oil production. Purpose of those tanks is to lower viscosities for injection and proper flow. We replaced them. You can kind of see in the picture. We've actually replaced the traditional fuel-fired, gas-fired tubes, which is very common in this application, with electrical heating. That's all fine and good, but it still doesn't matter, because the piping is the massive heat loss. Lee mentioned supports and stuff. You still are going to require, if the tank doesn't require heating or has an alternative heating source, you're still going to require heat trace to and from all the piping. And you can, obviously see our stuff in the warehouse, or in the shed there, before they install it on all the interconnecting piping. And then in the end, good insulation and good, thermal profile is the goal of all of this. So we're not 100% the answer, but we're certainly a part of it. And that's the discussion you have with the customer, and certainly a value to add to them. Some other examples really quick before I finish up, and I know I'm running long, and I apologize for that. Separation tanks are quite common in the oil and gas world. You'll have these, not only upstream in the production side of that, through the midstream all the way to refineries. Certainly a place for heat trace and all of that. You can see the three-phase separators on the right. What is that? That's your petro, your raw product out of the ground. You're separating it for gas and water. Why send that in the pipeline when you don't need it? Then you have to pump that off and address it, and heat trace falls a big part of that. What does that look like? Quite frankly, it's a lot of heat trace, right? In remote locations, it's certainly electric. All that monitoring, valving, piping. I mentioned the sand catchers. You can see them on the right of the picture of the gentleman with the blue hat. All of that gets heat traced. It's just oil and gas market is actually a good opportunity, and a good. We have a really good solution how to do that. You may notice, and I won't get too far into the detail, that valve on the top left. The layout's not much different than Lee illustrated earlier about, first of all, we're going to need more cable for larger heat sinks, and then how you kind of wrap it around. It will expand and contract with temperature. And there's a certain craft to the layout and install of the cable, and I can touch on that in further trainings, or we have trainings available on site. But again, winter's coming. You will find our cable, whether you see it or not, is under the insulation, and that's some more examples of how they install that. Even with a gas-fired system, as you see on the right, all the piping to and from that ends up being either electrical, or in some cases steam when steam's available. So back to the install, it's again fairly similar to what you may be used to with steam tracing, although again, ours is wire, and you lay it out. You want more wire to the larger heat sinks and supports and all that. Lee had mentioned the location. It's no different with heating cable. You do want it on the bottom of the tank because heat rise, or bottom of the piping because heat rises. You want to go to the outside where outside of the turns in your 90s. And there's install videos and training, and it's really simple after you get used to it and you start putting it together. You want to add extra loops and serviceability. I preach this all the time to the contractors installing our stuff about having service loops for splicing and other reasons, but also, when they go to, when heat tracing, after heat tracing is installed and off and running, where you're going to get problems about maintenance and all that, is not because of the heat tracing, because once it's up and running and it's in good shape, it'll be like that for years. It's usually when they go back and have to replace a valve or change some piping or disconnect something, and they cut the trace. That's when we'll have to, go out and replace it and be like, look, you can't just cut it. Then termination, stuff like that. Anyway, there's a lot more on that available to you. We have design software you can download off our website. So we talk about bill of materials and connection kits and end seals and all that. Same profile as steam tracing. You're gonna, BTUs are BTUs. You're gonna do the heat loss based on the pipe size and the insulation, the application, and then the thermal input can either be the steam or the electric. Our software also, we can pull out and design and offer ISOs, so installation instructions, and then walk through with that, which is really handy. I mentioned before, there's a lot of videos and stuff available. Troubleshooting one's actually a lot of fun because you get to see where things go wrong, but then in doing so, you also learn from that. So that's a lot of fun, and I invite any of you to check that out. There's like I mentioned, a lot of sales training and design training available to you, and I welcome any of you to reach out to me. I will certainly provide you with the links and stuff, how that goes together, if you would like to learn more. So with that, I will wrap up and open up for any questions for Lee and I on this introduction to heat tracing for oil and gas. Thank you all.